fourth program is to build an artificial neural network and implement the backpropagation algorithm. And we also test the algorithm by giving an appropriate input. Backpropagation algorithm contains two phases, forward phase and the backward phase. Forward phase, which computes the functional signal and carry forward the input till the end in the network, and backward phase, which computes the error signal and propagates the error backward through network starting at output unit. Backward learning algorithm is divided into multiple steps where we need to calculate what is the number of hidden node input. We need to compute hidden node output. We need to compute input to the output node and also compute the network output. And then at the end, we compute error between the output and desired output. Once you compute the error, we need to modify and adjust the weight accordingly between the hidden node and output node. And also we need to modify the weight between input and hidden node. So this slide represents the diagrammatic representation of a neural network to show the forward phase and backward phase. In our program, we give the required input representing in the input values like 2, 9, 1, 5, 3, 6, and we display this in the form of an array as a floating point value. We see the first column 2.9, 2.0, 1.0, 3.0, and the second column 9.0, 5.0, 6.0. We need to normalize the input, so here the input contains two columns. The very first column I have to find out which is the max value, and for the second column also I need to find out the max column. To find the max, I call upon the function called a max that takes upon different argument. Here this a max shows the syntax of function where the very first argument represents the array name and the axis which represents whether it is a column or row. If axis value takes upon 0, then it returns an array containing maximum value for each column. If axis value takes 1, then it returns an array containing maximum value for each column. So if axis is equal to 0, we extract the max value for column. If axis is equal to 1, we extract the max value for each row. So here in this slide you can see x is equal to x divided by np dot a max, which is nothing but a max, where x is equal to 0, indicating that we extract the max value of a particular column. So 2 divided by 3, which is 0.66, 1 divided by 3, which is 0.33, then 3 divided by 3 is 1. Similarly, the second column, the max value is 9. So if it is 9 divided by 9, it's 1.0, and 5 divided by 9, it's 0.55, and 6 divided by 9, it's 0.66. Next, we also initialize what is the output we expect for the given input. So the output is, we have given y is equal to 3 different value, 92, 86, 89. And to normalize the output, I divide every output value by 100. 92 divided by 100 is 0.92. What the expected value, output value is? 86 divided by 100, 0.86. 89 divided by 100 is 0.89. So the neural network which I'm considering to understand this program, where my input layer contains two input nodes. In one single hidden layer consists of 3 hidden nodes, and there is one output node at the output layer, and we have a bias which is input to the hidden nodes. Now we are going to make use of random module from NumPy package because it contains many functions for the generation of random numbers. To generate a random number from the normal distribution, I can call upon the function normal, And if I want a specific size for the random function to be generated, we specify that by using size. For example, in this slide we have given size is equal to 4. So in our program, the weight of the hidden node we need to compute. To compute the weight of the hidden node, I call upon the function uniform from the random package, and the size is nothing but the hidden layer neuron. So we have two neurons at the hidden layer, and the other one is hidden layer neuron. So input layer neuron is 2 and hidden layer neuron is 3. So it is 2 comma 3. And we also calculate what is the bias at the hidden node. So the bias at the hidden node, again we are finding out by calling upon the function uniform, and we have given the size is equal to 1 comma hidden layer neuron. So hidden layer neuron is 3. So it is 1 comma 3. Next, we need to calculate what is the weight at the output and bias out. So similarly, we call upon the function uniform and we specify what is the size. Size here is equal to 3 comma 1. And for bias output, we are again calling upon the function uniform and size is equal to 1 comma 1. I also call upon the function dot. Here this returns, dot function returns the dot product of any two vectors, say for example A and B. So dot product usually can handle 2D array, but considering them as a matrix, it will perform the matrix multiplication. So according to our program, this is X represents the normalized input, and we have calculated what is the weight of the hidden node. We have calculated what is the hidden node input. So to calculate the hidden node input, I am calling upon the function dot. Next, to the hidden node input, I am adding upon the bias value. And then we have given a definition for the sigmoid function. So the sigmoid function is computed that returns a value that is 1 divided by 1 plus exponential to the power minus x. So we again call upon the sigmoid function and we just calculate what is hidden layer activation, and we also calculate what is W out and out input node. Again we call upon the sigmoid function for each of the out input node. Next we calculate what is the error output. Error output is equal to y minus output, that is y is our computed, that is what we have calculated, minus the output. So now once this is computed, we have to traverse back again from backward phase from the back to the input node. So we need to compute what is weight output. Once we computed weight output, then we call upon hidden gradient by calling the function derivative sigmoid. Then once we calculate the weight of the hidden node, next we can print what actually is the input, what is the actual output and the predicted output. Thank you.